evaluate the integral of z over 16 minus z square into z plus iota over the circle C, which is given to be as mod z equal to 5. Now here, if you put the denominator equal to 0, we are going to get the points z equal to negative iota and plus minus 4. And because the given circle is having the radius 5, which means all these points are lying inside this circle, right? So instead of working on the partial fractions, we are going to apply the Cauchy's theorem for multiply connected regions. And for that, we need to construct the 3 circles for these points inside the circle C, right? So it is very easy to use that theorem for this integral. So let's start with the solution. So this is your given integral, and this is the circle C with the radius 5. And I can write z over 16 minus z square into z plus iota as, because if I take the fractions, I'll get 4 minus z and 4 plus z and z plus iota. To avoid 4 minus z, I need to write this as z minus 4, and here negative sign appears in the numerator for this, and this can be written as z plus 4, right? So clearly, this z over 16 minus z square into z plus iota is analytic everywhere except at z equal to, when putting the denominator equal to 0, we are getting the points z equal to, yes, plus minus 4 and minus iota, right? And all these points are lying inside the circle. This is plus minus 4 and here it is negative iota, right? Okay, so clearly this is analytic everywhere except z equal to plus minus 4 and negative iota, and these points lies inside the circle mod z equal to 5. So to apply the Cauchy's theorem for multiply connected regions, we are going to construct 3 circles around these points. Let's construct the circle C1 around the point z equal to 4, and this is your C1. And let's construct the circle C2 around the point z equal to minus 4. This is circle C2. And let's construct the circle C3 around the point minus iota, z equal to minus iota. This is your circle 3. So the first circle is C1 with radius R1, let's say. And the second circle is C2 with radius R2, let's say. And the third one is having the radius R3, let's say. So circle C1 is mod of z minus 4 equal to R1 because it is constructed around the point z equal to 4 as center. And the circle 2 is mod of z plus 4 having the radius R2. And the third circle is z plus iota with radius R3. And we have constructed these circles such that the intersections of C1 and C2 is of course phi, and C1 and C3 is also phi, and C2, C3 is phi, right? So then, by Cauchy's theorem for multiply connected regions, the given integral is equal to, yes, the integral over C is equal to the integral over C1 plus integral over C2 plus integral over C3, right? Let's write further this as, we have written the numerator as minus z, and here we are writing z minus 4, z plus 4 and z plus iota. I can write like this, plus the second integral over C2, again writing minus z over z minus 4, z plus 4 into z plus iota. And then the third integral over C3, minus z over z minus 4, z plus 4 and z plus iota, right? Okay, so in the first integral, because this integral is over C1 and z equal to 4 is lying inside the circle C1, so we have to take our fz to be as minus z over z plus 4 into z plus iota, right? And for the second circle, because this circle is constructed, C2 is constructed for the point z equal to minus 4, so here we have to take our function to be as minus z over z minus 4 into z plus iota, right? And for the third circle, because C3 is constructed having the center as z equal to negative iota, so for that we are going to take the function as minus z over z minus 4 into z plus 4, right? Okay, so for the first integral over C1, I am taking as the function fz, and for the second integral I am taking the function as, let's say, gz, and for the third I am taking the function as hz. Here it is written over here what is fz, gz and hz, right? Is it clear? Okay. Okay, now we are going to apply the Cauchy's first integral theorem over here, right? Now since fz, gz and hz are analytic inside and on C1, C2, C3 respectively, and the points z equal to 4, minus 4 and minus iota are inside the circle C1, C2, C3 respectively. So therefore by the Cauchy's first integral formula, the given integral is equal to, yes, what is the formula for that? Okay, let me write this again. This is fz over z minus 4 plus gz over z plus 4 plus, and this integral is having hz over z plus iota, right? And by Cauchy's first integral formula, the first integral is equal to 2 pi iota times f of 4, right? So this is equal to 2 pi iota times f of 4. Should I write the formula for you? Okay, the formula is integral over c f of z over z minus z naught dz is equal to 2 pi iota into f of this point z naught, which is lying inside the circle, right? So for C1 circle, the point z equal to 4 is lying inside the circle. So this integral is equal to 2 pi iota f of 4 if you match the result with this theorem, right? Okay, plus 2 pi iota, and for C2 I am having z naught as minus 4 because it is z minus z naught. So z naught is minus 4 over here. So this is g of minus 4. And then for the third integral, z naught is minus iota. So I am having 2 pi iota into h of minus iota. So taking common 2 pi iota, and inside I am having f4 plus g of minus 4 plus h of minus iota. We just need to put the values of z. Okay, what is f of 4? F of z is minus z over z plus 4 into z plus iota. So f of 4 becomes, so from here, f of 4 is equal to, yes, minus 4 over 4 plus 4, 8 into 4 plus iota, right? So writing this value over here. So this is minus 4 over 8 into 4 plus iota, and I'm also rationalizing this, 4 minus iota over 4 minus iota plus, okay, what is g of minus 4? From here we get g of minus 4 as, yes, it is 4 over minus 8 into minus 4 plus iota. Okay, so writing here 4 over minus 8 into minus 4 plus iota, and then rationalizing this as minus 4 minus iota over minus 4 minus iota. Fine. Okay, then is h of minus iota. So from here we get h of minus iota equal to, yes, this is iota over minus iota minus 4 into minus iota plus 4. So writing here iota over, just simply this is a minus b and a plus b format. So this become minus iota square minus 4 square, right? So this is 2 pi iota, alright. So this will go by 2. This is minus 4 minus iota divided by twice. Okay, this is a plus b, a minus b, that is 16 minus iota square, which will become 17. Then again this will go by 2. So this is minus 1 over 2. And here it is minus 4 minus iota. So let me manage this sign. So this becomes 1 over 2 into 4 plus iota, right? Divided by, again this is a plus b and a minus b format. So this will become minus 4 whole square minus iota square, that is 16 minus iota square, which is 16 minus of minus 1, that is 17 again. And for the third one, this is iota over, okay, a square minus b square. So this is minus 1 minus 16, that is minus 17. So this is equal to further 2 pi iota over, let me take this 17 common. So I get 17 as common from the denominator. So this is minus 4 plus iota plus 4 plus iota divided by 2 minus iota. So minus 4 and 4 cancelled out. So here I am having 2 iota over 2, that is iota. So this is equal to 2 pi iota over 17, and here I am getting iota minus iota. That is equal to 2 pi iota over 17 into 0, which is finally comes out to be as 0. So the solution for the given integral is 0. So this is how we apply the Cauchy's theorem for the multiply connected regions to avoid partial fractions, right? Okay, thank you. God bless.